Good morning, everybody. So as Phil said, we are a pediatric hospital that does genomic medicine. We are in the clinical state, so we are actually able to make an impact on children's care. So can I get a show of hands? We're going to have some audience participation. How many of you have kids? All right, keep your hands up. How many, those who don't, how many know a kid? All right, great. Everybody, I think so. All right. So I want you to kind of use your imagination. You're going to put on your thinking cap. So you probably remember the day that your child was born. At least I hope you do. And those people who don't have children, maybe you remember the day that your friend's child was born, or maybe your niece or nephew was born, and how exciting that day was for the mother and father. So you get up in the morning, like in my personal experience. She got up in the morning because my wife had two giant children, so she had to have C-sections on both of them. So we had them scheduled early in the morning. We got up and went to the hospital, and I remember the feeling of walking down the hall, and almost the smell of the hospital, the smell of the maternity ward, and the lighting of the room, and you get prepped and you go into the operating room, and you're sitting behind the curtain, and just kind of, what's happening, and finally the moment arrives, and your child is born, and your mind is racing, your emotions are completely out of control, and you may be smiling, you may be crying, you may be screaming and yelling, you never know. And then this is where things take a little bit of a turn. You hear the doctors talking, and the nurses, and then your baby's whisked away, and you don't get to see him or her, and you finally imagine that for a second. Your baby's whisked away without you seeing them, and the doctors and nurses can't really tell you what's going on yet because they don't know, and but things don't look quite right. Maybe your baby might have some sort of breathing problem or whatever. Take your pick. And then they come in and say, "Well, we've had to take your baby to the NICU." And you finally, maybe after an hour or two, you get to look behind the glass and see your baby in a state similar to this, with constant supervision on all kinds of machines, and in fighting for its life, basically. So this is an incredibly emotional time for these families. So later on, weeks go by. You spend the first 2 months in the NICU with your child, fighting for its life. Things start to get better. Things may take downhill turn momentarily, or may get better much faster. Then you're released from the NICU, and then you go home, and the doctor says, I want you to come back every week. We need a follow-up visit every week. So you go back, tests are run, some invasive, some not so invasive, some painful for the child, some painful for the parents. All the while, you still have no answers. So after a couple months of these weekly visits, you might get to come back down to maybe a monthly visit. Still more tests are ran, and still no diagnosis. And then maybe they're to 3 months visits, and then 6-month visits, and then yearly visits. By that time, there could be massive damage being done by the disease to your child that they don't know what's going on. So that's traditional medicine, which has given us many, many, many great things. I don't want to dog on traditional medicine by any means. It's been a it's changed the world, given us vaccines, cures for some diseases, while others remain a mystery. And this is pretty much us looking under the lamppost, because we've only had a small vision into what causes some of these diseases. Enter in genomic medicine, which the size of the data that we generate really is why we call it big data. And in HPC, if you can tell, this is the Earth with all the satellites around it. These are it kind of shows you we have a much wider array, wider vision on what causes these diseases now. So I want you to, for a second, go back to that mental image of your child in the NICU. And now with genomic medicine, not all the time, not 100% of the time, but roughly 52%, I believe, is the latest number, we're able to make a diagnosis, a molecular diagnosis of these genetic diseases. So, which ultimately, excuse you, or bless you, which ultimately leads to less time in the NICU, less stress on the parents, less stress on the baby, and a lot of those invasive, painful procedures, those tests that are done, are pretty much wiped away. So a human genome is roughly 22,000 genes, and it codes for roughly 100,000 proteins. And that is, those are some numbers that we can kind of get our heads around. 22,000, 100,000, those are pretty easy to kind of comprehend. But then when you talk about actual base pairs, you have 6.4 billion, with a B, letters in your genome, which, if you're a fantastic typer, it would take you roughly 50 years to type that many letters. And that's a really, really big stack of papers. So the Lady Liberty is roughly 305 feet tall, which is how large your stack of papers would be. I don't want to type that much. So again, that's a lot of data. That's a lot of data to sift through. So, gotta have some memes. We're the meme generation, right? So, what do we do with the data? We've generated it. How do we store it? Well, we store it in, obviously large tier 1 type storage. But one of the things that I've been kind of very, very surprised about is the curation of data in other research entities that I've worked with. Curation in this data, I mean, you have file types that you need for publication and just for analysis. You have to know where those are. You can't have them strewn about the entire system. So you have to have a standardized location to make these things manageable and also for automation. When you have automation built into the system, that makes things much easier on the IT side, but also on the analyst side, so they know exactly when data is coming off the sequencers, when the data has been variant called and ultimately archived, so they can take up the analysis job. So when the data is carefully curated, you're going to see a drop in disk usage. In my particular area, we saw probably about a 20% drop in disk usage. So it also makes it easier for forecasting and backing up. So one of the big things that I've heard with big data is how do we share this data? And in the past, since we deal with not only clinical data, we also deal with research data. We shovel a lot of data around the world to other centers so they can help in analysis. But in the past, we used disks. We would hook a disk up and chuck all the data onto the drive and then call FedEx up and ship it out. Which, if other researchers around the world are waiting for the data, that could take 4 or 5 days depending on where in the world it's going. So at CPGM, we've invested heavily into the infrastructure and bandwidth in order to do this over the line, and I think ultimately it's going to speed things up probably quite a lot. This also allows for, again, more automation, which will kind of allow us to trickle the data out instead of this giant flood of data, which we use for, which we were accustomed to when we used the drives. So here's a couple of our awards and some of our notoriety for the work that we do. We were on the top 10 Time Magazine for 2013 for medical breakthroughs with our genome sequencing for critically ill newborns. So there's more questions that are being raised with genetics and genomics in particular. With new technology that comes out, we're obviously going to be generating more data, and what do we do with it? Especially with, like, say, the new X10 sequencers, which are, I believe, able to do something like 18,000 genomes in a year. I may be slightly off on those numbers. And then also we're seeing a new technology coming in the hardware space, particularly things like the Edicode Dragon BioIT processor, which promises to do an entire genome in 30 minutes for variant calling and analysis. So those are some fairly exciting new tech advances that we're hoping to implement here in the center. That will eventually let us to go sub 24 hours on a genome, on a whole genome, which currently right now our fastest sequencing tech is pushing just under 50 hours for an entire genome, from sample taking all the way to diagnosis to the patient's family. So there are roughly 8,000 genetic diseases that we know of. In the U.S., 1 in 30 children are believed to have one of these genetic diseases. So you can look at this picture, and there's roughly 30 children there. Pick any one of them, and you can probably guarantee that one of them has a genetic disease. This also, 1 in 6 is causes for hospital admissions. And then 1 in 5 deaths, just in Kansas City alone, is attributed to one of these genetic diseases. So the hard facts, we know less than 5,000, we know the cause of less than 5,000 of these diseases. And diagnosis often takes years, and this is unacceptable for the family, and ultimately should be unacceptable for society as a whole. Like I mentioned earlier during my initial story, when a child is waiting for a diagnosis, a lot of times the disease lays waste to their body or their mind, and with quicker diagnosis and quicker treatment, that can ultimately change the child's life forever. It could mean something as simple as, they may not have heart attacks every day. So traditional testing, we could only do between 1 and 20 genes per test, and time to result was 1 to 3 months, and that's fairly acceptable. But it was very lamppost driven again. It was a very finite group of genes that they only were able to test for. But with genomic testing, next-gen sequencing, we're able to do 500 to 22,000 genes, and the turnaround time to diagnosis is days to months, and months really is the worst-case scenario. The reminder here is to think back when we did the first genome. Took something like 10 years, something like that. So 10 years to days. It's a pretty good speed up, I think. And something also that's very exciting is we are able to discover new disease genes, which a lot of my coworkers at the center are focusing their entire career around. So what are we finding? Well, a couple case studies. There was a male, 7 years old, who had progressive weakness in his muscles. He'd been seen, I believe, something like 35 times before by other specialists, still with no real diagnosis. And at Children's Mercy, the clinic noticed that 2 of the siblings also had poor muscle tone. After genomic sequencing, we found a very simple cause to the problem. And there was a compound heterozygous variant in the nebulin gene, and it seemed to be that it was an autosomal recessive Nemeline myopathy type 2. I'm not a medical guy, so I'm very excited that I actually got that out. Okay. And again, we were able to sequence both that boy and his siblings and found that they all had the same variant. And one of the great things about this story is in the past with traditional medicine, it would have meant that there were biopsies, muscle biopsies. And I don't know if any of you have ever had a muscle biopsy. I haven't, and I'm really, really thankful I haven't. But I know it's extremely painful, which in this instance makes Mom very, very happy that her children did not have to go through that pain. So again, 35 specialty visits with no diagnosis prior to coming to the center, with studies costing roughly around $35,000. With genomic sequencing, that cost only $3,248, and one specialty visit for their siblings. So that's pretty much a paradigm shift. Baby 2, we saw that there was a fetoprotein, alpha fetoprotein deficiency in the mother at 16 weeks. And then during an MRI, we found that the baby had multiple issues, including scoliosis, and the hydrocele was ruptured. Right after he was born, he was admitted to the NICU with a ruptured ophthalmocele, and shortly thereafter developed acute liver failure. And when a baby of this pre-existing problems goes into acute liver failure, that's generally the outcome is death. The parents were counseled, and they were counseled that it did not look very good for their child. Well, in come the Genome Center as a kind of last-ditch effort to help save the baby's life. We did confirmatory testing after genomic sequencing. This was one of our 50-hour tests because time was critical. We then were able to administer corticosteroids and immunoglobulin, and the liver function returned to normal. And now the baby is home and well. The only thing is, unfortunate, we weren't able to find the cause of its genetic abnormalities. Genomic sequencing is wonderful, but it's not infallible. This one's particularly rough because this little baby boy, at 4 days old, his identical brother died at 4 days old from the same disease. And he was transfused at birth multiple times, and he continued transfusions over the next 3 months. And during one of those, during that time, he went into cardiac arrest, and we just about lost him. And through that 3 months, another $30,000 in workup. We found out that there was one other person in the world that had this exact variant, genetic variant, and we found that we needed to do a transplant. And ultimately, he's better now and home and cured. So does it make a difference? Yes, it absolutely does. Again, like I said, there's roughly a 52% home run, as we like to call it. So there's still strikeouts, but we're getting better all the time. These are a few of my vendor partners that that we absolutely cannot do this without. And part of my team that I work with, these people are some of the most brilliant people I've ever met. Thank you.
Any questions? Yes.
Fascinating. It was really good. So one of the things you mentioned was 52%, that it's increasing. What has it increased from? How long you guys have been doing it, and how long it has gotten to be 52%?
Well, the increase is very very slow. When I first started giving these presentations, I believe it was somewhere around 47, 48%. So it's very, very gradual.
And when was that? 47?
Oh boy, yeah, probably late 2013, I think, maybe. Uh-oh.
So Shane, you talked about the last case where you actually had an N of 1 that you found. How did you, was that within your network or was that outside? And if it was outside, how did you find that other patient so that you knew that you needed to do a transplant? Because one of the problems is the sharing of data generally isn't done. We've got a lot of data globally, but it isn't necessarily available so that we can find those easily.
Right. That would be on the geneticist side, that they were able to find it through papers and things like that. That wouldn't have been in our, that wasn't in our hospital that it was done originally. I'm pretty positive that that's what.
Could you compare and contrast your EMC Isilon usage and your Data Direct networking usage from your last slide there?
Well, we'll talk later.
Shane, when you mentioned that you had invested in infrastructure to get data out faster, like pipes and things,
Yeah.
have you invested in technology that allows remote users to log in, keep the data at rest, and do their run their algorithms against the data without moving it?
The data that goes out is really data that's already been computed. It's
so you
ready.
would consider it a product that goes out?
Yeah, you could consider it that. Yeah, it's a finalized data file that is sent off to collaborators or whatnot, and so just very large very large chunks of data that they want to open up in some sort of graphical viewer and view the entire genome in comparison to the reference type of a thing.
Okay, well, I had experience with being able to do similar type work with people logging in remotely, getting the raw data, process it in the way they're making a product, visualizing it, analyzing it, and then sending the very last piece of results back to their constituency.
Security at the hospital doesn't allow external people to come in and do that kind of thing. So that's kind of our only way of doing it. And I think really a lot of our collaborators are looking for new diseases and really don't want to look at a subset of the data. They want to see the entire chunk that came off the sequencer. So it's almost like they want to have the second opinion almost.
Shane, hi. Thank you. It was very insightful. Obviously, we shared a ride yesterday. So
yeah.
Obviously, you've solved, or you guys are addressing some of the problems that we've been talking about, whether it's storage or the infrastructure, because
Sure.
this obviously requires obviously significant investments. Just, and without naming vendors, we don't want to obviously get into, but from your perspective, maybe just share some of your best practices, right? Obviously, you've gone through the last couple of years sort of addressing. So some of the things that, you found were useful or helpful from an infrastructure perspective. Just share some of those, best practices or feedback.
Oh boy.
Thank you.
Well, I think that's a very long, broad conversation. But as far as storage goes, I mean, we haven't actually purchased, or we haven't actually got DDN in-house yet, but DDN has actually helped us kind of realize that they are the way to go. Isilon, again, as people have said here, is more of an enterprise thing. It's more of an enterprise storage system. And Illumina has used Isilon for a very long time. But I think that's slowly merging away as HPC is kind of seen as a necessity in genomics, and I think that's why DDN is really coming in and sweeping up. So, but as far as data sharing, again, we went with DDN also because they will allow us to share data much easier and faster, and like their WAS product, we're able to have sister sites and share data that way. So there, we can talk a lot. We can chat later more about it.
In today's world, 6 billion letters doesn't sound like all that much. So could you explain a little bit what takes up the time in the processing and analyzing these sequences?
Sure. Well, I can try to at least. So we, my genome is roughly 4%, or no, 0.04% different than yours. And so you have 6.4 billion letters, and those letters compared to a reference, you're going to see deletions, you're going to see insertions into that mix. You're also going to see inversions. And you're also dealing with chunks of the sequence. So sometimes the aligners, the algorithms that are used, have trouble reconciling those deletions and additions and inversions, which can really eat up a lot of time. That's really a large chunk and a large reason, a large problem in the genomic space. I think maybe does that answer your question?
Is it that you're comparing genes so that you have to shift and compare different parts?
Yeah, kind of.
So earlier in your presentation, you had proposed, do you store the genome in the patient file? So taking that a little bit further, what are the ethical compliance concerns, and then how are you approaching them from an IT perspective when you look at projects like this, especially in a hosted environment at DDN, and doing the HPC computing for the genome? What are the ethical implications long term, as this is brand new space that hospitals and medical facilities are just embarking on?
Yeah. So you're referring to child has this disease that we're dealing with now, but we find something else in the genome, or we
No.
hold on to it for later on, or?
Well, if you're going to store the genome in the patient's file, and if you think about it from a big data perspective, that information is going to never go away. So as that child grows, changes, as we start modifying how people are credit scored, now we're going to have healthcare scores that are also going to be measured. What are the long-term ethical implications that the medical community is perhaps considering with regard to the information they have, patients' privacy, and then how those implications may bear out over time?
We're still figuring all that out. So the center was granted an NIH grant for $5 million for 5 years, and part of that, half of that money, was put directly towards ethical questions. You know, what do we do with this? Is this actually working? You know, all of those types of things that you're asking. So that study is actually being done now, and we don't have any like concrete thing to say, hey, here it is. But we have. It is, and there's also, like I was mentioning, you know, you have the baby, and you find that the baby has this particular genetic defect, and we're able to kind of we're working on that problem, and we may solve it, we may change diagnosis, we may change treatment, but during the analysis we find that the baby has the BRCA1 gene. BRCA2 gene, you know, testicular cancer, breast cancer. You know, how do we reconcile that? How do we not tell, you know, the mother and father that your baby has this giant chance of having breast cancer or testicular cancer later on in life? How do we do that? That stuff is all being fought out in ethical studies, and I really hope that I hope they find something soon, and I hope they're able to at least start, you know, divulging some of that information soon.
Yeah, so I have one question. So when you're actually trying to find that particular gene for that particular disease, we all know that you have to have a population of multiple patients, so that you do comparative study, you can find that gene.
Sure.
How big is your sample size?
I think we have a couple thousand samples that we've done so far.
Okay, and then how long does it take for you to analyze those samples?
Analyzing, depending on if it's a stat-seq, which is our 50-hour test, or our large panel test, which is really takes about a week of sequencing. So it could take, you know, between 2 days and 2 to 3 weeks, depending on the situation.
That's for single sample process, right?
Single sample for stat-seq, multiple sample for the larger gene test.
Okay, so that's my question, because I'm in the medical space, and FDA approached us, asked us to look at like 200 some algorithms for next generation sequencing. Initially, we only used 5 algorithms to start with. Same thing, we have 500 patient samples. But once they go up to 270 algorithms, we eventually put in 2 million CPU hours. This entire scale up is a big challenge. So that's why I'm so curious about how you are handling that.
We use kind of the big data view of it all. So we do the data curation. We have medical experts that are actually doing data curation before tests are even ran. So they're mapping genes to disease what do I want to say? How diseases show themselves. I'm at a loss for the word. To genes, and so then we have that database that's already built, and then once we're able to during initial viewing of the patient, the doctor is able to say that, this child has, say, sloped forehead, or, a shorter middle finger, or those kind of characteristics are then mapped to gene diseases. And then we kind of, we use sort of a Gantt chart procedure, where you have say three different genes, or three different characteristics that you're looking at. And we have a set of, say, 3 genes that go along with those characteristics, maybe 4 genes, maybe 5. And then kind of in the middle, you have a particular gene that you can focus in on. And then we sequence just that portion. So we're doing kind of big data analytics before we even go to the compute side, and even before the sequencing side. So we know where to pinpoint before we even sequence. And then we sequence just for that particular gene. And then once we're past that, we go into the compute side. It's much easier, because then we can align only that portion of the reference to that gene.
So basically, you're not really processing 6 billion base pair. You're really just processing a very, very small portion.
Yes, yes.
Shane, thank you.